everyone, welcome back to the channel. So in the previous session we have discussed about general characteristics and uses of lanthanides. So therewith we have completed lanthanide concept. So yes, in web block element, what is another series we have? It is the actinoids, right? Yes, in this session we try to understand a little concept about actinoids. Yes, what are actinides? Yes, actinides are also one of the series. One of the series of what? A series of F block elements. Here, in case of actinides, the differentiating electron enters into what? Differentiating electron enters into 5f orbitals. Okay, the differentiating electron enters into 5f orbitals. Therefore, actinides are also called what? 5f series. As like lanthanides are called 4f series elements, here actinides are called 5f series elements. Okay, well, now the actinides includes what? Again, actinides also includes how many elements? 14 elements. From what? From thorium to lawrencium. Thorium Th, lawrencium Lr. Then what about the first member, actinium? Okay, actinium. So actinium is not a true F block element as like a lanthanum. Here actinium is not a true F block element, but most of the properties of this actinium, it going to correlated with the properties of a F block elements. Therefore, actinium is included in a 5F series while studying. Okay, yes, actinides. The actinides, there are 14 elements. Actual actinide starts from thorium to lawrencium. Okay, well, now these actinides are generally what? They are generally radioactive elements. So remember, actinides are generally radioactive elements. Okay, yes. Then if you consider their electronic configuration as well as uh, oxidation states, first we consider the electronic configuration. So all the actinoids have the electronic configuration of 7s2. Means we said here 5f 1 to 14, okay, 6d 0 to 1, 7s2. Now here, if we look at the outer electron configuration of actinoids, say all the actinoids have electronic configuration of 7s2, means in all those 14 actinoids, 2 electrons are present in 7s orbital. And what about 6d and 5f? Yes, there is a variability. The variable occupancy of 5f and 6d subshells. Okay, there will be change in the number of electrons in 5f as well as in 6d. But what about 7s? It always going to have 2 electrons in all the actinoids. So just I repeat the sentence what it is. All actinoids have the electronic configuration of 7s2 and variable occupancy of 5f and 6d subshells. Well, the irregularity in the electronic configuration of actinoids, as like in case of lanthanides also we have observed certain irregularities. Similarly, here also we observe irregularities. Yes, the irregularities in the electronic configuration of actinoids, like those of lanthanides, are related to the stabilities of F0, F7 and F14 configuration. So if we consider 5f orbitals, yes, even we observe here also certain irregularities in the electronic configuration, means expected and observed electronic configurations are different. Okay, why we are getting that irregularity? Means it is because of stability associated with the F0 configuration, F7 configuration and F14 configuration. So F0 empty more stable, F7 half filled, okay, half filled, it is also stable. And what about F14? Is a completely filled, so it is also more stable. So why we are getting irregularities, why we are observing irregularity in their electronic configuration means it is because of a stability, or I can say it is in accordance with the rule of stable configuration, right? So the extra stability associated with the F0, F7 and F14 occupancies of the 5f orbitals. Okay, well, now if we consider the elements their atomic number, symbol and electronic configuration, okay, and their oxidation states. Well, when we analyze here, say elements, atomic number 89, actinium, AC is the symbol. Say outer configuration, so 5f0, there is no electron in 5f orbital, so 5f0 6d1 7s2. 5f0, there is no electron in, okay, f orbital, so actinium is not a true a block element. Then if you consider its ionic radii how much in its +3 oxidation state, it is 111 picometer. The next one, thorium, atomic number 90, Th is the symbol, okay, 6d2 7s2 5f1. Then what about its in +4 oxidation state, its ionic radii is 99 picometer. So atomic number 91, protactinium, Pa is the symbol, so 5f2 6d1 7s2. So if we consider +4 oxidation state, 96 picometer is the ionic radii. Then 92 atomic number, uranium, so U is the symbol. Then what about electronic configuration, 5f3 6d1 7s2. Then in +3, if I consider 5f3, if we consider electronic configuration of +3 ion, so 5f3 is the configuration. Then in +4, 5f2 is the configuration. There will be 3 electron and 4 electrons, right? Then in +3 oxidation state, its ionic radii is 103 picometer, and in +4 oxidation state, uranium is going to show 93 picometer as its ionic radii. Okay, well, then atomic number 93, neptunium, Np is the symbol. Then electronic configuration in its elementary state, 5f4 6d1 7s2, right? Then +3 means, say these 3 electrons were lost from 6d and 7s2, remaining 5f4. Then +4 means 5f3, right? So neptunium. Then coming to the next, 94, plutonium, Pu is the symbol, okay, 5f6 7s2, that one electron from D 6d, one electron is transferred momentarily to 5f, so it becomes 5f6 6d 0, actually 6d 0 and 7s2. And if you consider M3 in +3 oxidation state, what is the electron configuration? It is F5, 5f5. Then in +4 oxidation state, it is 5f4. Then if you consider ionic radii in +3 oxidation state, it is 100 picometer. Then coming to the 95, atomic number 95, americium here, say Am is the symbol, Am. So electronic configuration, its elemental state, 5f7 7s2. What about 6d 0, 5f7 6d 0 7s2. So here 5f7 means, we know about orbitals, right? How many orbitals present? 1 2 3 4 5 6 and 7 orbitals present. 7 orbital means here 7 electrons. So what about all 7 electrons? All 7 electrons are unpaired electrons. So if I consider atomic number 95, americium, how many unpaired electrons present? 7 unpaired electrons present. 5f7 means all 7 electrons are unpaired. So please remember this, americium 5f7 6d0 7s2, all 7 electrons are unpaired electrons. Okay, yes. So in elemental state, we said 5f7 7s2. Then if you consider +3 oxidation state, it is 5f6 and +4 5f5. Okay, yes. Then considering ionic radii, if you consider the ionic radii in +3 oxidation state, it is 99 picometer, and in +4 oxidation state, it is 89 picometer. Well, next one, 96, atomic number 96, it is the curium. Curium is also one of the important thing to be remembered. So curium, Cm is the symbol. Then if you look at the electronic configuration here, so americium has 7 unpaired electrons, right? Now in this case curium 5f7 6d1 7s2, so totally 7 plus 1, there are 8 unpaired electrons. So curium is the element having the highest number of unpaired electrons. Okay, atomic number 96. Well, now in elemental state we set the electronic configuration 5f7 6d1 7s2. Then if I consider electronic configuration of a plus 3 oxidation state, it will be 5f7 6d0 7s0. Then in plus 4 oxidation state it will be 5f6. Then coming to the ionic radii, it is 99 picometer in plus 3 oxidation state and 88 picometer in plus 4 oxidation state. Then atomic number 97, it is berkelium, Bk is the symbol, 5f9 6d0 7s2 in plus 3 oxidation state, 5f8 in plus 4 5f7. Okay. Then coming to the ionic radii, 98 picometer and 87 picometer. Then 98, atomic number 98, californium, Cf is the symbol, electronic configuration 5f10 6d0 7s2 in plus 3 oxidation state, it is 5f9. Then in plus 4 oxidation state it is 5f8. Okay. Then coming to the next one, 99, atomic number 99, einsteinium, Es is the symbol, electronic configuration 5f11 6d0 5f11 6d0 7s2 in elemental state. Then in plus 3 oxidation state it is 5f10, 3 electrons are lost, right? 2 electron from 7s and 1 from 5f. So after losing 3 electron, going to be have 5f10 configuration. Then in plus 4 it is 5f9 is the configuration. Then if you consider ionic radii, so then 100 fermium, Fm is the symbol. Then what about electronic configuration? 5f12 7s2 in elemental state, 5f11 in plus 3 oxidation state, 5f10 in plus 4 oxidation state. Okay, means dash indicates their ionic radii are not exactly measured at. Okay, well, then atomic number 101, mendelevium, then Md is the symbol, 5f13 7s2, 5f13 6d0 and 7s2 is the electronic configuration in its elemental state. Then plus 3 5f12 plus 4 5f11. Okay, then 102 is the atomic number, that is nobelium. Nobelium, No is the symbol, electronic configuration 5f14 6d0 7s2, 5f14 6d0 and 7s2 elemental state. In plus oxidation state it is 5f3 13, in plus 3 oxidation state 5f13 is the electronic configuration. Then in plus 4 oxidation state 5f12 is the configuration. Okay, then last one, lawrencium, it is the Lr is the symbol. Then elemental state 5f14 6d1 7s2, 5f14 6d1 7s2 is the electronic configuration. In plus 3 oxidation state 5f14 is the electronic configuration. Then in plus 4 5f13 is the configuration. So here, when you consider the electron configuration, yes, what we observed, yes, there is always 2 electrons present. There is always 2 electrons present in 7s in its elemental state. But what is the variation? Only with respect to 5f and 6d orbitals. The electrons are variable in 5f and 6d orbital changes, but there is no change in the electrons in 7s orbital. 7s orbital always going to have 2 electrons, while there is a variation in the number of electrons in 5f and 6d orbitals. And what is to be remembered here, and which element, that is the element having highest number of unpaired electrons, it is the curium with atomic number 96. So what is the configuration? We said 5f for Cm. Okay, atomic number 90, atomic number 96. If I consider curium, So what we said, 5F7, 6D1, 7S2. So totally how many? There are 8 unpaired electrons present in curium. Okay, well, so it is regarding electronic configuration, that is in elemental state, in +3 oxidation state, and even in +4 oxidation state, and even we considered the ionic radii in +3 and +4 oxidation state. Okay, well, now coming to the ionic sizes, or I can say ionic radii, there is a gradual decrease in the size. As like lanthanides we said, there is a steady decrease in the size of, okay, size of lanthanides from lanthanum to lutetium, right? Similarly here also in case of actinides, there is a gradual decrease. There is a gradual, or I can say steady decrease in the size of atoms or M3 plus ions, means in +3 oxidation state across a series. This steady decrease in the size of actinides from actinium to lawrencium is called actinide contraction. So as like lanthanide contraction, here we are saying actinide contraction. So what is actinide contraction? Actinide contraction is nothing but it is the a steady decrease in the steady, or I can say gradual, or I can say continuous, a gradual decrease in the size of atoms and atoms, or I can say +3 ions, M3 plus ions across a series from actinium to lawrencium is called actinide contraction. Okay, well, the contraction is greater if you consider the magnitude of actinoid contraction, magnitude of actinoid contraction is greater than lanthanide contraction. So if we consider magnitude of actinoid contraction and lanthanide contraction, where the magnitude is more means the magnitude of actinoid contraction is greater than lanthanide contraction. Yes, why it is so means, so if we consider lanthanides, okay, 4F 1 to 14, 5D 0 to 1, 6S2. Coming to the actinides, 5F 1 to 14, 6D 0 to 1, 7S2. Now 4F 5F. So on comparison, say the greater from element to element, that is the actinide contraction is greater from element to element in this series, resulting from poor shielding effect by 5F electrons, which means if I compare shielding effect of 4F and 5F electrons, 4F electrons have more shielding effect on comparison. 4F electrons have more shielding effect than 5F electrons. Or in another words, I can say 5F electrons have very poor shielding effect compared to what? 4F electrons. Therefore, what happens? That contraction, actinide contraction is greater compared to lanthanide contraction. Okay? Yes. Now regarding oxidation states, as I said here, yes, actinides have a large number of oxidation states because of very small energy gap between 5F, 6D and 7S subshells, or I can say orbitals. Okay. Lanthanides also shows variable oxidation states. Yes, actinides also shows variable oxidation states. So here actinides have a large number of oxidation states, even +8. Okay, because of very small energy gap between 5F, 6D and 7S subshells. Okay, yes, and these actinoids show the general. What is the general oxidation state or common oxidation state? It is the +3. Lanthanides also shows +3 oxidation states. Actinides also shows a +3 oxidation state as their common oxidation state. Okay, yes, the elements in the first half of the series, frequently exhibit higher oxidation states. Okay, well, then the maximum oxidation state first increases up to middle of the each series and then decreases. If you consider maximum oxidation state, it increases up to middle of the series, thereafter decreases. So look at this. We'll just analyze here the variable oxidation states exhibited by actinoids. Well, say actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. So these are the actinoids. Now actinium, the first member of the family, they show +3 oxidation state. Protactinium also shows +3 oxidation state. Uranium, neptunium, say up to what? Up to lawrencium. Thorium, it do not show a stable +3 oxidation state. So actinium, except thorium, all other members of a 5F series, they show +3 oxidation state. Then thorium shows +4 oxidation state, a stable oxidation state. Protactinium, uranium, neptunium, plutonium, americium, and all up to berkelium, they show +4 oxidation state. These are the stable oxidation states exhibited by the elements. Then coming to this protactinium, uranium, and neptunium, they even show what? +5 oxidation state. Plutonium also shows +5. Americium also shows a +5 oxidation state. Then coming to uranium, say when you look at mid of the series, what I said, from actinium to middle of the series, oxidation state increases, tendency to form higher oxidation state increases, thereafter what happens? Decreases. Well, now say uranium, neptunium, plutonium, americium, they even show what? They even show +6 oxidation state. These uranium, neptunium, plutonium, and americium, they are present at the middle of a series. They show even +6 oxidation state. And coming to neptunium and plutonium, they even show what? They even show +7 oxidation state. Got it? Yes, if you consider oxidation states, yes, actinides also shows variable oxidation state. That oxidation state increases till mid of the series and thereafter decreases. Well, then coming to the MCQs, say which actinoid exhibit a highest oxidation state? Actinium, plutonium, uranium, lawrencium. Yes, what is that? Plutonium. Plutonium shows a highest oxidation state, that is +7 oxidation state. Yes. Next one, which actinoid has highest number of unpaired electrons? Highest number of unpaired electrons, just I already specified that. What is that answer? Curium, Cm is the element having highest number of oxidation state. How many unpaired electrons present here? There are 8 unpaired electrons. If I consider 5f7, 6d1, 7s2, so totally there are 8 unpaired electrons present. So answer curium. Well, so with this I am going to conclude about this session. Again in the next session we go for another concept. Thank you. Be safe.